Okay, welcome everybody. Thanks so much for joining me today. My name is Brandon Minnick, and in this session we're talking about correcting common async await mistakes in .NET. Now, buckle up because we're going to be moving really fast today. So don't worry about trying to take notes or memorize anything, because like I said, we're going to be moving quickly. But the good news is I've already taken all the notes for you. If you take out your phones and head to this URL, it's my website, codetraveler.io/async await best practices. That QR code takes you to the same spot. That's where you can find a recording of this talk. It's where you can find the slides. It's where you can find links to NuGet packages I'll be recommending, links to open source libraries that we'll be demoing in the talk today, and a whole bunch of more links for if you want to continue learning async await, because it's going to feel like we're going really deep into async await today. We're only scratching the surface. There's so much more to learn that we can even cover in 60 minutes today, but let's get started, because when I was dry running this earlier, it took me about an hour and 20 minutes, so we're going to cram it down into an hour. All right, let's start out by looking at this async task method called getLibraries. This is going to go out to a public API using HTTP client, deserialize it, and return its value. But what's really happening here with async await? Well, let's say thread 1 kicks off this method. So thread 1 comes in here, it initializes this variable called response, and then as soon as thread 1 hits this await keyword, it returns. And HTTP client.getAsync is going to run on a background thread. So in this case, we'll say it's running on thread 2, but it could be running on any available thread that's available in the thread pool. And this is really, really good, because we don't want thread 1 making this API call, because thread 1's a very, very important thread. It's also known as the main thread. It's also known as the UI thread. And it's the only thread in our app that can draw the UI on the screen. It's also the only thread that can respond to user input. So when the user taps a button, it's thread 1 that responds. When the user scrolls a list, it's thread 1 that redraws everything on the UI. So if thread 1 were to be running HTTP client.getAsync, and let's say this API call takes 5 seconds, then thread 1 would essentially be busy. It'd be doing something else for 5 seconds, and the user would be tapping on our app, but our app would be completely frozen. So the good news is we're using async await. And this is going to be running on a background thread, which is exactly what we want, because now thread 1 is free to return and interact with the user. Now, when it's done, thread 1 jumps back in to run the next line of code. It initializes this variable stream. And again, once it hits this await keyword, thread 1 returns. Well, we read the content from the HTTP response on another background thread. So we'll say this is thread 5, but again, it's whatever thread is available in the thread pool at the time. So thread 5 finishes, thread 1 jumps back in, and just like we expect, we hit the await keyword again. We have another background thread to deserialize that stream. When that's done, thread 1 jumps back in again, make sure that it's not null, and as long as it's not null, returns the results from our HTTP call. Now, to really understand what's going on here, we need to jump into the compiler-generated code. So what I've done is I have gone to the website, sharplab.io, and it's not shown on the screen. Here, let's see. Built-in display, main display. This should be. There we go. All right. OK, so jumping into the compiler-generated code. We're here at sharplab.io. This is a really, really cool website, really, really powerful website. Highly recommended if you've never heard of it. In fact, the .NET team even uses this website when they're creating new features for .NET, so they can see what it looks like in real time, just like we're about to do today. So what I've done, I've taken that code that we just walked through a minute ago, and we have that here on the left. And on the right side, we have the compiler-generated code. We have all this extra code that we didn't write. Our code takes just a couple lines here. But on the right, this is all compiler-generated. And so what we're going to do is we're going to look at how async await actually works under the hood. Because one of the interesting things about .NET was created before multi-threading was even a thing. Back when C# and .NET first came out, every CPU was just a single core processor. There was no concept of having multiple threads. And so what the .NET team had to do is essentially create this functionality for a framework that was never designed for it. And that's why we get all this code here on the right. So let's jump into it. The first thing we're going to see here is it's created a struct called getLibraries with some angle brackets and some underscores that inherits from async state machine. And fun fact, if I were to switch this to debug, and we look at the debug build, in debug, it's a class, and you'll notice there's also some extra variables here, like here's our HTTP client on the right, here's our HTTP response message, response, and our content stream. But in release mode, the compiler optimizes those away because we really only need those variables to exist when we're debugging, when we need to know the result of the response when we add a breakpoint to it. So in release mode, it generates a struct called getLibraries that inherits from async state machine. And if we scroll all the way down, we actually see down here the same method definition that we created. So public async task, or in this case on the right, just public task of type library model called getLibraries. But you'll notice inside of the method that we created is none of our code. So what's happening now is when this method gets called at runtime, when our method that we defined, getLibraries, gets called at runtime, what's really happening under the hood is it's initializing a state machine for us. So what we see here is it's creating the state machine and initializing a couple variables. An important variable to note is it sets the initial state for our state machine to -1, and then it starts it and returns a task that this task will be completed whenever either our state machine is finished, or if it faults and throws an exception, that's also when this task will return. So let's jump back up to that state machine. So scrolling all the way back up here, we have getLibraries, and most importantly, we have this method called moveNext. Now, this was something that was strange to me when I first started using async await long time ago, because I would see moveNext all the time in stack traces, and I was always like, what's this moveNext method? Like, I never wrote a method called moveNext, but I see it every time I get an exception with async await, and that's because it's compiler generated. And basically what happens with moveNext is this is our state machine. So moveNext is a giant switch statement. And you can see we have a couple cases. So we've got our default case, and then case 0, case 1, case 2. And basically every time we use the await keyword in our code, it adds another case. So we use the await keyword 3 times here. That's why we have case 0, case 1, and case 2. And so let's look at what's going on here. So first things first, moveNext initializes this local variable num to the current state, which, remember, when it initialized, this is -1 to begin. So that means when we enter our switch and we go to -1, that means the first thing we're going to do is enter into this default case in our switch statement. And finally, this is where we can start to see our code again. So this is where we finally call getAsync, and there's some optimizations going on here. So .NET saves it. It actually gets the awaiter of the task and saves that to this variable called awaiter. But something really cool happens right away, because .NET knows that sometimes tasks are already completed. So if a task is already completed, do we really need to switch threads? And so what it does first is says, hey, is awaiter 3, is getAsync already completed? Because if it's not, we're going to have this, we see this goto statement. We're going to go to line IL007E, and if we scroll down, IL007E essentially moves on to the next line of code. So this is where we would get the result from getAsync. This is where we say result.ensure status code. And so essentially, if the task is already completed, we don't need to switch threads. We can just keep going. So we get a little performance bump for free thanks to the compiler and the .NET runtime. But in our case, we know that we're calling a public API that's on the internet. There's no way this task is going to be completed. So we know we're going to enter this if block where the first thing we do is we update the state. So we change the state to 0, which means next time we come back in, we're going to jump down to case 0. We'll save awaiter3 as a global variable here. So we've got a bunch of global variables defined, and this is angle bracket u under _ 1, but this is just our HTTP response message. And then we tell our state machine that, hey, we are going to wait on the result of that awaiter. So we're essentially letting the state machine know we're waiting for get async to finish, and then we return. And this return statement is how thread 1 is able to return back to the user, and we are able to free up that calling thread. So then what happens is once awaiter3 is done, once get async has completed, we jump back in to our switch statement. So we jump back into move next, and we reinitialize all the local variables, and we grab our state, which is now 0. And this is how thread 1 knows to jump back in where it left off. So it jumps back into state 0, where it does a little bit more initialization again. So it grabs awaiter3 from that global variable. We do essentially a little garbage collection here, where we essentially set that global variable back to its default value of probably null. That way the garbage collector can clean it up if we want. And then it sets the state to -1, temporarily, just in case. And finally, now we go to IL007E. So this is the same go-to statement that we would have gone straight to if the task hadn't completed or had completed already. So now we jump down to 007E, where, again, we get the result. We double-check the status code, and then we hit another await statement in our code, where we're going to read the content as a stream. So same, right? We're going to get the awaiter for read a stream async. We're going to check to see if it is already completed. If it is, we'll just continue on. We won't return. We won't switch threads. But if it hasn't, then just like last time, we're going to update our state. We're going to say, hey, the next place you're going to jump back in is going to be state 1 or case 1. We'll assign that global variable, and we'll let it know that, OK, now we're awaiting this variable called awaiter2, which we know is just our read a stream async. So again, when that finishes, we jump back in. We go straight to case 1, and we do the same thing all over again, right? Like we grab the value from our global variable. We set that global variable back to the default, so the garbage collector knows to get rid of it. We temporarily set the state to -1, and then jump down to IL00E7, which, just like you expect, because we're hitting another await message, is now going to grab the awaiter for deserialize async, check to see if it's completed, and we'll do it all over again. We'll update the state to state 2. We'll set the global variables. We'll let it know, hey, state machine, we're now waiting on this awaiter. And again, when that's done, just like you expect, we jump straight to case 2. We do it all over again, but the difference here is now we break. So we're finally done with all of our async await statements. So we finally break out of this switch. And this is where we finally get to set the value of our list of type library model. We double check to see if it's null, because if it is, we'll throw that exception. And if it's not, we move on, assigning the value to result 3. And eventually, we come down here where we set the state to -2. And then finally get to set the value of the task to the result 3, which is our library models. So really cool stuff here, because again, remember, .NET was created before any of this asynchronous programming stuff existed. So this is kind of crazy to look at, but also pretty beautiful how the C# team was able to give us just async await. We get this nice readable code, and they kind of do all this for us on the back end. Now, one thing I want to highlight is you'll notice there's a catch block here, which means there's also a try block. And if I scroll up, and we keep scrolling, scroll, we'll see that this try catch block is essentially the entire code. So all the code we wrote in our async task method is inside of a try-catch block now. But again, I didn't write a try-catch block in my code. This is all done for us by the compiler every time we create a async task. And what this means is that if any of my code throws an exception, like maybe get async returns a 500, so that's going to throw an exception, well, that exception gets caught here. And it's saved as the value, saved to the task as an exception. But I didn't write a try-catch block, so I don't really expect an exception to get caught. However, the compiler is doing that. Now, the good news is, as long as we await this task, so as long as when we call get libraries, we say await get libraries, that await keyword will rethrow this exception for us. But if we don't await the task, then this exception gets swallowed up forever, and we never see it as a developer. And this is probably the biggest cause of bugs that I see when I'm reviewing PRs implementing async await, because I'm guilty of doing this myself, where when I first started using async await, I thought I was being really clever, right? I'd be like, I want some code to run on a background thread, so I'm going to say task.run, I'm going to type in all my code, and I'm not going to await it because I don't care when that task finishes. But what I didn't realize is my code was throwing an exception. It was trying to make an API call just like this. It maybe sometimes couldn't because I'm a mobile app developer, so sometimes people are using my app on a bus and the Wi-Fi's bad or whatever it might be. So my code was throwing an exception. I didn't await that task, so that exception got swallowed up here inside of the try-catch block, and I never saw it. And you might think to yourself, like, hey, isn't that a good thing, right? Like, exceptions crash my app. I don't want exceptions. But actually, exceptions are good because we want to see those as developers. We want to be aware when something exceptional happens, when something unexpected happens in our code, so that we can handle it. Because what I should have been doing was catching that exception and probably displaying a little pop-up to the user, letting them know, hey, try a pull to refresh again because your internet connection doesn't look good, or also probably resetting some variables in the code, gracefully handling that exception. But because I wasn't awaiting my task, I never even knew that exception existed. And it was the hardest bug to figure out because I'd be looking at stack traces, I'd be looking at my app, and my app's now in this weird state where like the internet or the API call never came back, but the app thinks it did, and so everything's kind of garbled. I'm like, how did this even happen? Because I didn't write code that allows this, and it just turns out that exception was just getting swallowed up in my task. So anytime you see a pull request comes through, or Monday when you get back to work and you look at your code base and you see that you're not awaiting a task, fix it. Fail that PR. Those is such a bad anti-pattern. Probably the worst one I see is people say like underscore equals task.run. And just gives me the shivers, because, again, you're never going to get an exception out of that, and you're just going to have the worst bugs to try and figure out. So this is this is definitely the biggest gotcha with async await, that because the C# team did such a good job, because we're able to write elegant code like this, we would never know that under the hood we might be missing out on exceptions, because they're getting swallowed up inside of this try-catch block. OK, so quick review. The async keyword adds about 80 bytes. And that's because every time we use the async keyword on a method, the compiler takes that and generates all that extra code we just saw, turns it into a struct. Unless you're still in debug config, then it'll be a class. And this is more of a fun fact than anything else, because we're talking about 80 bytes, not 80 megabytes, not 80 kilobytes. We're just increasing the file size of your DLL by 80 bytes every time. So does that really matter? For me, I make mobile apps. Mobile apps are usually hundreds of megs. Do I really care if I get a couple extra bytes? Probably not. But if you're working on something that's maybe embedded or an IoT device, that may matter. But good to know that every async method becomes a struct. And actually, in .NET 8, this was optimized. I think it used to be 96 bytes. But literally, the .NET team went in and was able to remove a couple lines of code in that compiler-generated struct. And now it's only 80 bytes. So fun little performance improvement for all of us for free. And we want to await every task. So like we were just talking about, non-awaited tasks hide those exceptions. So if bad things happen in our code, we need to be gracefully handling that as developers. But if we don't await the task, we'll never know that it happened. So again, it sounds good on the surface, right? Like no exceptions, our app's never going to crash. But in reality, it's just going to be a bad user experience. It means the user's going to be left with an app that's like half working because it assumes something completed when it hadn't. So we always want to await every task. Okay, so let's jump into some code. Enough talking about this stuff. Let's actually check out an app that I have. So this is an app that I've made using .NET MAUI, and I'll show it to you. We're running on iOS, it runs on Android, it runs on Mac Catalyst and Windows, and all this app does is pulls down the top stories from a website called Hacker News. So Hacker News is like a tech blog where you can find all the latest stuff in the tech world, and pretty simple app. All it does is pull down the top stories, and if I click on any of these, it takes me to the article so I can read it. Now, what we're going to do here is we're going to fix some code. And like I mentioned earlier, don't worry about memorizing anything, because everything we're going to be working on is in this bad async await practices class, whereas everything's already been fixed inside of good async await practices. So sit back, relax. You don't have to worry about writing anything down. It's already fixed for you. But what we're going to do is go through and find all these to-dos where we're going to refactor this code, we're going to fix it, and we're going to make everything better. So let's get started right here. In this first one, we are inside of the constructor. So this is the constructor for my news view model, and I'm calling this refresh method. And I'm already getting yellow squiggle. .NET's already yelling at me, and it's interesting to me because I'm not awaiting this task. So that's what the yellow squiggle is. But I really wish they would update this warning. Actually, I worked at Microsoft for 7 years, and I spent so much time campaigning on this because the warning just says, this call's not awaited, so the current method continues before it's completed. And you go, well, yeah, that's why I'm not awaiting it, duh. But what I wish it would say is, and if this method throws an exception, you're never going to see it. Good luck. But for some reason, I think, well, just my opinion, the .NET team is almost too deep into the weeds, because literally when I would pitch that, they'd say, well, why? Everybody already knows that. why would we need to put that in the warning? So, well, we all know it now, and you can share this with your friends and coworkers on Monday, certainly. But right, so I want to call refresh, because this refresh method, this is what gets called when the user does a pull to refresh. So when a user comes in, does a pull to refresh, this is the method that goes out and gets all the stories from Hacker News. And I'm calling it here in the constructor, partly as an example to show off some stuff here, but also because I want the user, when they launch the app, to see all the stories. I don't want the user to load the app, be greeted with a blank page, and then have to manually refresh. That'd be a terrible experience. But what do we do, right? Because we're in a constructor. And I literally just said to everybody here, we always need to await every task, but we can't use async await in a constructor. We'll likely never be able to use async await in a constructor, because constructors are just meant to initialize objects. They're literally setting aside a location in memory to put this object, and we use it to assign a couple variables, but we should never, ever be doing any long-running tasks in a constructor. We should never await a new creation of an object. That'd be crazy. So one thing we could do is I could make another method called refresh, and then down here, I can await that method, and then back in my constructor, I can just call refresh. And look at this, no more yellow squiggles. This totally works, but I can kind of feel the tension in the room right now, because we just created an async void method. And what are we taught as .NET developers? Never use async void, which it's not bad advice, because actually, this is a valid use case for async void. Now, I'm not advocating that we all go out and use async void, and I'm going to explain why in a bit. But async void is essentially a fire and forget method. So if you don't care when a method completes, and that's why we use it for things like event handlers, because event handlers just fire, and then they don't really care what we do when we handle them. So here, yes, technically, this is a valid use case for async void, because we're doing a fire and forget. But why is this dangerous? Well, the first reason why async void's dangerous is let's think about that threading example we saw earlier, right? So let's say thread 1 initializes the constructor. So thread 1's going to come into here. Thread 1 enters the refresh method. Thread 1 hits this await keyword, and then it returns. And it returns back to here. So we'll say thread 1 continues here. And what if I did some stuff like this? Like, I'm going to clear my top story collection. I'm going to maybe add something to it. And meanwhile, this refresh method's running on a background thread, and this refresh method is also clearing the top story collection and adding stuff to it. So with async void, we've literally just injected a race condition here, because now we have two threads modifying the same collection. Which one's going to win? Probably thread 1's going to win 99.9% of the time. But again, now you're going to have a weird bug to have to track down, because you're going to have a user going, hey, sometimes the top stories don't appear. And you go, OK, well, can you reproduce it? And they go, no, because it's a race condition. So async void, dangerous because we can accidentally inject race conditions to our app. The other reason async void's dangerous is, let's say this does throw an exception. So we could pretend like refresh is going to throw an exception, but why not just hard code it in there, right? So this is definitely going to throw an exception. So you might think to yourself, well, hey, no problem, right? I'll just put refresh inside of a try catch block. I'll come back here, and I'll handle it. No problem. Well, again, think about what's going on. So thread 1 initializes the constructor. Thread 1 calls refresh. Thread 1 comes down to here, hits the await keyword. Thread 1 returns. And it returns to the next line of code, which is the end of the try catch block. So now thread 1 is down here, and we've exited the try catch block. And when this exception gets thrown, we're never going to be able to catch it. So this is the other reason why async void is dangerous, because you'll almost never be able to catch an exception from an async void method. Now, what's really, we'll say the worst part about all of this is when we use IntelliSense, IntelliSense tells us, or rather, IntelliSense doesn't tell us that this is an async void method. And so, yes, the refresh method is like, it's right here, right? Like, as a developer, you're like, how can you miss it? It's right there. But let's say maybe it's in another class. Maybe another developer wrote an async void method, and we're consuming it, but we don't know it's async void because we're just relying on IntelliSense. And totally fair. As C# developers, when we look at this in IntelliSense, we see that this is a private void method. It is absolutely safe to assume that refresh will have completed before this line of code runs. Totally valid assumption. There's nothing wrong. I will never fault anybody who makes that assumption because, well, the person who made the async void method is wrong in this case. So yeah, with async void, it becomes really dangerous here because, again, we won't be able to catch exceptions from it. We're going to possibly create race conditions. And it's really just not going to help future us or fellow developers on our team because IntelliSense doesn't let us know that it's async void. So yes, people are right when they say never use async void. However, I argue that the advice should be to just avoid async void. It's not bad, but as long as you know the dangers, then that's where you can start using it, although you probably shouldn't. So jumping back here, so we're not going to use async void. We can't use async await. But again, I just said we've got to await every task in case this throws an exception so that we can handle it. Well, what do? So I've created an extension method called safe fire and forget. And if we dig into the source code for this extension method, what it's doing is essentially exactly what we just did with async void, but it's providing all the guardrails for you. So you don't have to know anything about what we just talked about, or when that junior developer joins your team, they don't have to know how the async state machine works or anything about that. They'll see the safe fire and forget method, and it's very obvious, it's very intuitive that you're calling out that I want to move on to the next line of code before this finishes. And also, you can even handle exceptions. So if you want, you could say trace.writeLine, pass in the exception, or whatever it might be how you want to handle it. You can still handle those exceptions gracefully. So Highly recommend using Save, Fire, and Forget. I know I'm biased because I created it, but it is available on NuGet. The library is called Async Await Best Practices, and we're up to 1.7 million downloads, which is really mind-blowing to me because this is just a fun helper method I created, and now I'm seeing it being used at companies like Mozilla. So super, super cool. And also, I'll say, shameless plug, if you want to learn .NET MAUI, highly recommend it. I love it. And in fact, I just published a course here on dometrain.com. So Dometrain is one of the sponsors of our event today. And on Dometrain, you can find this .NET MAUI both getting started class, where this teaches you the basics, how to create your UIs, how to use .NET MAUI. Then also, I've created a deep dive where we go into concepts like how do you make GraphQL API calls for .NET MAUI? How do you use SQLite databases with .NET MAUI? How do you use Async Await with .NET MAUI? That's all available for you, too, on dometrain.com as well. So back to the code. So finally, we're done with that. We've got our Save, Fire, and Forget method. We know that the next line of code is going to run. So we'll say thread 1 continues here while refresh is running. We're still awaiting the task under the hood, because again, down here, in Save, Fire, and Forget. Oh, that's down there somewhere. That's OK. We still await the task and handle it for you. So got all the guardrails in place. All right, next refactor. So coming down to this method refresh, again, this is what fires anytime a user does pull to refresh in my app. The first thing I want to highlight is we're accepting a cancellation token. Anytime we create an async task method or a value task method, we always want to have a cancellation token as a parameter, because when other people call our code, they need to be able to cancel it. And for numerous reasons, but for something like this where a pull to refresh is happening, I don't want the user sitting there for 20 seconds if they're on a bad internet connection, just watching this little spinning indicator. So what I do is I pass in a cancellation token that maxes out at about 5 seconds. And if the cancellation token fires or completes, then I'll do a little pop-up that says, hey, looks like you got a bad internet connection. Try again later. But as good C# developers, if we are creating a method that returns a task, we always want to make sure we pass in a cancellation token to help our teammates, future developers, or developers that might be using our libraries. So coming down here to refactor this, I'm getting yelled at here because, in fact, I'm not forwarding that cancellation token. So task.delay actually does allow me to pass in a cancellation token here, which is great. So shout out to those developers for following best practices. And what I'm doing here is I'm actually kicking off a task that's going to last for 2 seconds. And this looks a little weird, but what I'm doing in my app is saying, hey, anytime you do a pull to refresh, I want it to last for at least 2 seconds, which sounds crazy because what if the API call comes back in 1 second? Well, now we're wasting the user's time. But in reality, if that API call happens too fast, then the UI might update, and the user would never see that spinning indicator. And as crazy as it sounds, because they're actually getting it faster. They're getting it so fast that they don't even need to see the indicator. That's the indication to the user that we got their pull to refresh action. So in mobile apps, it's super common to do this, where we set a minimum time of usually 1.5 to 2 seconds so that they can see that spinning indicator. And so later down, when this method's done, I'll await this task later to make sure that that spinning indicator is displayed for at least 2 seconds, let the user know that we acknowledge their pull to refresh. But what I want to show you something that's pretty cool here is, it's just saying, anytime we create a async task method, we should always have a cancellation token parameter. But is that really the case in the real world? No. There's libraries out there that I've used that don't let me pass in a cancellation token. What do I do? Well, there's this cool new extension method called wait async that we can pass in our cancellation token here. And wait async basically bolts that cancellation token onto the task that we're using. So if you ever find yourself in this scenario where you're using somebody else's code, they didn't allow you to pass in a cancellation token, well, no worries. Microsoft and the .NET team's already solved it for us with wait async. We can essentially just bolt on that cancellation token to whatever task we're using. But in this case, task.delay allows us to pass it in there, so we'll just do it the best way here. OK, the next refactor. We have this method. We're getting the top stories. And then once we get the top stories back, we're going to iterate through this for each loop and add them into this sorted collection. So this looks pretty good, right? Like we're using async await, just like we talked about. But again, let's think about what's happening with async await. So let's say the user does a pull to refresh. So that's a UI event. That means thread 1 is going to kick off this method. So thread 1 is going to come in here. Thread 1 is going to hit the await keyword, return. Get top stories is going to run on a background thread. Great, that's exactly what we want. But then thread 1 comes back when that's done and continues running this code. So thread 1 is now in this for each loop. And what if there was 500 top stories? What if there's 5,000 top stories? Well, thread 1 is going to be locked up in this for each loop, adding them into this sorted collection. So this is not great, because now we're overutilizing thread 1. And if it is 5,000 stories and that takes 2 seconds to get through this for each loop, well, our app's going to be frozen for 2 seconds. So that's really bad. So what we can do is we can say .configure await false. And configure await false is basically tells .NET, I don't want to return to the calling thread. So the default is configure await true. So if we don't put anything here, by default, .NET will return to the calling thread. So configure await true is what causes thread 1 to come back in here and run these next lines of code, because thread 1 is what kicked off the task. It was the calling thread. Configure await false lets .NET know, hey, I don't care what thread we return to. When I'm done, just go to the thread pool, find whatever thread is available, and let's continue on that. So configure await false here gives us 2 benefits. The first being, when we get to this for each loop, we're not locking up thread 1 for a couple seconds if there's 5,000 stories it's got to iterate through. And also, we'll see a little bit of a performance bump, because if we have to return to the calling thread, well, that also means we have to wait for that thread to become available. So this is a pretty simple app, right? Like, we're just pulling down news stories. But think about, like, what if it was a game? Maybe it's a game running at 60 frames a second, 120 frames a second. Thread 1's going to be really busy redrawing the UI 60, 120 times a second and handling user inputs. And so if we said configure await true here, or even nothing, because that's the default, we've got to wait until thread 1's no longer busy to come back in and run the next line of code. So with configure await false, we can rest assured we're never going to return to the UI thread. We'll never overuse it. And we get a little performance bump because we don't have to wait for the calling thread to be available. So I highly recommend using configure await false. As a .NET MAUI developer, we use the MVVM architecture. And so everywhere in my view model, I know I'm never directly touching UI code. So I configure await false everywhere in my view model layer, everywhere in my services layer, anywhere where I know I never need that UI thread, I configure await false everywhere. Now, something cool new in .NET 8 is we also got these configure await options. So with configure await options, they gave us some really cool things, like one of them is forced yielding. Some of you may have heard of task.yield. So task.yield is how you used to have to do this. So task.yield basically says yield the calling thread, then return back to it. And these are super helpful, again, for me in mobile apps, because maybe I have a method that updates or needs to update something on the UI, so I change a variable, and I need to update the UI, so I would call task.yield to free up the UI thread so it can show that to the user. But here, with .NET 8, with configure await options, I can just pass in force yielding, and what this does is, if you remember when we were looking at the compiler-generated code, when we were looking here, right? We know .NET, the first thing it does is it looks to see if a task is already completed. And if the task is already completed, it won't switch threads. It's great. It's great for performance. We want that. But sometimes we do want to force that yield. We do want to switch threads. So force yielding essentially removes that optimization and says, hey, even if the task is done, even if we're just configure awaiting on task.completed task, still force that yield for me, because maybe I need to update something on the UI. Maybe I need to yield that main thread. So these configure await options are pretty cool because we can chain them together, because it's just an enum. So I could say force yielding and configure await options none. And configure await options none, these are interesting because There's configure await options none, and then there's configure await options dot continue on captured context. So continue on captured context is the same as configure await true, whereas configure await options none is the same as configure await false. It says I don't want to return to the calling thread. So that's a little weird. That still breaks my brain a little bit because it's a little bit new. But yeah, we can chain all these together. There's even this one here that, if I'm being honest, terrifies me, suppress throwing. So this says, hey, even if an exception happens, don't rethrow it, which I don't know when you'd want to use this, but maybe there's a scenario where you don't want that exception to happen. So with .NET 8, we get all these cool configure await options that we can chain together. And you also see suppress throwing today gives a little warning. It says it's only supported with the non-generic task. So you can't have a task that returns a result and use suppress throwing. So it has to just be task, not task of type T for suppress throwing to work. But I'm probably never going to use suppress throwing anyways. So to sum it all up, I'm going to stick with configure await false, and we'll call this refactor done. So now we know we're not returning back to the UI thread. We're running out of background threads here to iterate through our stories. Everything's great. OK, so now we get down to the finally block, and this is where we talk about that minimum refresh time task again. So again, this is just task.delay for 2 seconds to make sure that the user's going to see a spinning indicator. It's basically our way of acknowledging, yes, we got your user input. And right now, I'm calling .wait. Now, I have a rule of thumb, and it's never, 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 never use .wait. .wait is bad. .wait is really, really bad. What we should be doing here is just awaiting it. But obviously here for the example, we'll show we're using .wait. Now, the reason .wait is bad is unlike the await keyword. So we saw earlier when we use the await keyword, as soon as the calling thread hits that await keyword, it returns. But with .wait says, calling thread, you stay right here, and it locks your calling thread. Meanwhile, this minimum refresh time task is already running on a background thread. So for this one line of code, we're using 2 threads when we only should be using 1. And if this was our UI thread that was getting locked, well, now our UI thread would be locked for 2 seconds, and our app would essentially be frozen. So .wait is really, really dangerous because you can accidentally lock your UI thread. You can also cause problems with race conditions or where one thread might be waiting for another, but now it's locked up and it can't. But really with .wait, the big problem is it's using 2 threads when you only should be using 1. So a big problem in .NET is the thread pool is finite. There's only so many threads that .NET creates for us in the thread pool. And once you run out of threads, you reach what's called thread pool exhaustion. So if you have a super popular website or an API, you've probably seen this before. And if you're using .wait, because you're like, hey, I don't have a UI to worry about. It doesn't matter if my UI freezes because I'm just an API developer. Don't need to worry about it. .wait's still really dangerous for backend code because, again, you're going to use 2 threads every time. You should only be using 1. And you're going to reach that thread pool exhaustion twice as fast. So never use .wait for that reason. But I will admit, sometimes you have to, right? It's really rare nowadays, especially when we're writing in .NET 8. But sometimes there's an old interface that you have to implement, and that method on the interface returns a bool. And not a task of type bool, it returns a bool. So what do we do, right? Well, there's a better thing we can use instead of .wait, and that's getAwaiter, getResult. Now, getAwaiter, getResult does the exact same thing. This is still bad. This is still dangerous. It's still going to lock the calling thread. It's still going to use 2 threads when you only should be using 1. But with getAwaiter, getResult, we get better exception handling. So I don't know if you've ever seen it when you use .wait and your task throws an exception, it doesn't actually throw your exception. Your stack trace contains what's called an aggregate exception. So .wait throws this system.aggregate exception, which is an exception that holds exceptions, and then you just have to know to actually find your code. You got to dig into this aggregate exception, and it's a debugging nightmare. So getAwaiter, getResult does the same thing as .wait, but if your code throws an exception, it'll throw our code. So your stack trace will just be that operation canceled exception, whatever it might be, and you don't have to worry about digging through aggregate exceptions. So don't use .wait. But if you have to write synchronous code because maybe you're implementing an old interface, get await or get results the way to go. Now, here, we can just await it. We'll do configure await false. And yeah, fun fact, right? You can do async await inside a finally block. OK, next refactor. So let's look at this method here, get top stories. We are going out, we're getting the top story IDs from Hacker News. This is just the way the Hacker News API works. I can't just go to the API and say, hey, give me the top stories. I have to say, first, hey, what are the ID numbers for the top stories? And then I have to make another API call for each of those top story IDs to actually get the story. I think it's a terrible API design, but it is what it is. So that's what we're doing here. And if you can picture it in your mind, what's happening is, or as a user, the user is going to do a pull to refresh, and they're just going to see a blank page with a spinning indicator, and not until we've retrieved all the stories will they see them on the screen. So they're just going to sit there looking at a blank screen, spin, 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 spin for 5 seconds, and then bam, all the stories appear at once. So what we can do, we can actually make this better, and I'm going to cheat. I'm just going to jump straight to our good async await practices file. So what we can do instead is use an iasync enumerable. Now, maybe you've never implemented an iasync enumerable before, but you've probably seen it because iasync enumerable is what gives us the await for each loop. And this is really, really cool because it's essentially a for each loop, but we can await tasks. And as we get events back, as we get data back from the for each loop, now I can add these to my top story collection right away. So now instead of the user sitting there just staring at a blank screen, spin, spin, spin for 5 seconds, and then bam, everything appears on the screen, with a wait for each, we can essentially stream the data as it comes in. So as the API calls are completing, they're seeing these stories populate on the page, and it's just a better overall user experience. So with a wait for each, we can still use configure await. It looks a little funny here because you kind of tack it on the end like this, but it is what it is, and that it still works. And with iasync enumerable, again, it's an async method, so we always want to provide a cancellation token. But you'll see something new here, and that's this enumerator cancellation attribute. So let's say I remove this. You'll actually get yelled at. It'll say, like, hey, don't you want that enumerator cancellation attribute here? And the answer is yes, yes you do, because this is really cool. What enumerator cancellation attribute does is it tells .NET to say, hey, .NET, take this token, my token, and put it inside of your iterator. So every time that for each loop iterates, my cancellation token will get passed in, and .NET will check my cancellation token automatically for me. So what's really nice about this is, normally I'd probably have to come down here inside of my while loop, and I'd say something like token.throw if cancellation requested. But now we don't even have to do this because every time we iterate, every time we do a yield return, then it'll automatically check our cancellation token for us. So super, super cool, and pretty crazy that the .NET team came up with that. So that's how we'll refactor that one, and we'll just pretend like we did it here using iasync enumerable. All right, next up. We've got a method called getStory. So this looks pretty good, right? Like async, await. But one thing I see here is the only place we use the await keyword is in the return statement. And if I look at the definition for getStory, it returns a task of type story model. And here, we're also just returning a task of type story model. So something we can do is we can actually get rid of async, get rid of await, and we can just return the task. Now, this is going to feel a little weird and is going to look a little funny if you've never done this before. But again, if you think about what's happening, let's say when this method gets called with async await, the calling thread's going to kick off this method. Calling thread's going to hit the await keyword, return. We're going to switch threads. This is going to run on a different thread. When it's done, it's going to return back to the calling thread to return the value. And we've just did a couple of thread switches, a couple of context switches, when really we didn't have to. So by removing async and removing await, we can just return that task and allow whoever calls the method, that'll handle the thread switch there. So a little bit of a performance bump for us. And let's see, if we come back down, we've got one more refactor. And this is a method to get the top story IDs. And again, the only place we're using the await keyword is here in the return statement. So, should be pretty easy, right? We get rid of async, we get rid of await, and we'll get yelled at here because we have to say from result now, but that's okay. But this is actually a trick question because in this example, we're inside of a try-catch block. So if we think about what happens when this method gets called, as soon as we hit this return statement, we return the task and we exit the method. So what that means is we've left the try-catch block because we've exited the method before this task is completed. So this catch block will now never, ever catch anything because we're just returning right away. So yes, the only place in this method we're using the await keyword is in the return statement. But in this example, we definitely want to keep it because we're inside of that try-catch block. Now, one optimization we can do here is we can use something called value task. Value task is similar to task. It's not exactly the same. But the biggest difference is a value task is a value type, whereas a task is a reference type. And if you remember, reference types get initialized on the heap. Value types get initialized on the stack. And the reason value task is a little bit more performant is because adding something to a stack is just O of 1. It's immediate, super easy. Whereas when you add something to a heap, you have to index it, and it takes a little bit of overhead. And the reason we can use value task here is because we have a different return. So if we think about what's going on with this method, the first time the user does a pull to refresh, it will have to go get the data, because I have this is data recent checked. It says, hey, if you've done a pull to refresh in the last hour, I don't need to make another API call. I already got that data cached, so I can just return it. But the first time, we won't have that data yet, so we're going to hit the await keyword down here. But the second time this method runs, we're not going to use the await keyword. And the third time this method runs, we're not going to use the await keyword. And the fourth time this method runs, we're not going to use the await keyword. And so if you have a scenario like this where the hop path of your method does not use the await keyword, then you can return a value task instead, and you'll get a little bit of a performance bump out of it. All right. OK, so let's review all those awesome async await best practices, right? The first one, again, don't use .wait, don't use .result. We should always be using the await keyword nowadays. But if for some reason you have to write synchronous code, because maybe, again, you're implementing an old API or an old interface, then what you want to use is get await or get result, because you'll get a better exception if and when that task does throw an exception. You'll get your exception instead of a system.aggregate exception that hides your exception inside of it. Fire and forget tasks. So again, we need to make sure we await every task. And if we do want a task to, if we do want our code to continue on before, without awaiting it, then use say fire and forget. You can find it on NuGet as async await best practices. Avoid return await. So if the only place in your method you're using the await keyword is in the return statement, you can remove await, you can remove async, and you can just return the task. Save yourself a thread switch. Save yourself a little bit of performance. But again, if you're in a try-catch block, keep the return await. Same if you're disposing of an object. So if you're in a using block, keep the return await, because otherwise bad things will happen. Utilize configure await false. Like I mentioned, in my apps, anytime I'm in my view model layer, anytime I'm in my services layer, where I know I'm never touching and interacting with the UI or the view, I configure await false everywhere. The one caveat is there's something in .NET called a synchronization context. And again, if you want to learn more about synchronization context, I've got a link to it on the website that we have here on the slides. And in just about every .NET framework, Blazor, .NET MAUI, Xamarin, WinForms, WPF, a synchronization context exists. And the synchronization context is essentially what allows you to return to the calling thread. It's essentially what facilitates that. But in ASP.NET Core, there is no synchronization context. So in ASP.NET Core, configure await false is basically the same thing as configure await true. So little fun fact for you there. Also, we have configure await options. So these are enums. They can be chained together. We've got continue on captured context if you do want to return to the calling thread. We've got force yielding if you always want to do a thread switch, even if a task is already completed. We have suppress throwing if you're crazy and you don't want that task to throw an exception. And then also, and again, this one's the weirdly named one, none means you won't return to the calling thread. Value task. So just like we talked about, if your method's hot path does not use the await keyword, then instead of returning a task, you can return a value task and get a little bit of a performance bump without having to go through all the overhead of initializing a task. Async enumerable for streaming data, that's our await for each loop. Just remember, anytime you do it and you have that cancellation token parameter, include that enumerator cancellation attribute to allow .NET to use your token in its iterator for you. And then we've got .wait async. So again, if you have to use somebody else's code and they didn't allow you to pass in a cancellation token, it's OK now, because we can just say .wait async, and we can bolt on our cancellation token to their task, even though maybe they didn't include it as a parameter in their method. And lastly, async disposable. I didn't have a good example for this in the code, so we'll just go over it quickly here. Now we can essentially await the disposing at the end when we're disposing and garbage collecting objects. So this is really nice because certain objects like file stream, you have these big memory buffers. So when you dispose of a file stream, it's going to take a bit. And now with async disposable, we can do await using. And again, we can still use configure await false, so you can see it tacked down at the end. But I wanted to cover this because the syntax is a little funny looking, right? Because right here is the await keyword, but what really happens is we don't await until the end. So we enter the using block, we run all our code, and then it's not till we actually dispose of that object when we do the await and the configure await false. So keep that in mind, because intuitively you might think, OK, we're going to await up here, but really it's not till we dispose of it at the end when that await happens. OK, if you haven't gotten the chance already, now's the time to take out your phone, grab this QR code, which takes you to my website, codetraveler.io/async await best practices. Because again, this is where you can find everything we just covered. So I have a recording of the video of this talk, so you can share that with your friends and coworkers who maybe couldn't be here today. I've got links to the async await best practices NuGet package, where you can find the safe fire and forget extension method. I've got links to the source code for the Hacker News app that we went through today.